वेलकम टू द लॉस फंक्शन। यहाँ हम एआई, मशीन लर्निंग, मैथ्स और प्रोग्रामिंग के टफेस्ट कॉन्सेप्ट्स को सिंपल और इजी बना देते हैं। तो कंफ्यूजन को मिनिमाइज करो, नॉलेज को मैक्सिमाइज करो। चलिए कुछ एक्स्ट्रा ऑर्डिनरी सीखते हैं।
Welcome to this explainer. Today we're going to completely demystify how artificial intelligence actually learns. We hear a lot of buzzwords thrown around, but beneath all of it is a really fascinating, continuous loop known as the neural network training cycle. We're going to follow the exact journey of a single prediction, from the moment data enters the network to the precise moment the system corrects its own mistakes. Here's our roadmap for today. From neurons to matrices, making a forward pass, navigating the loss landscape, the calculus of learning, and finally, the magic of backpropagation. All right, let's jump straight into part one, from neurons to matrices. So our starting point is the classic biological neuron, right? You've got dendrites carrying impulses in and axon carrying them out. But here's the thing. To build AI, we don't literally simulate squishy biology. Instead, we use computational nodes. And in practice, we're not even calculating each neuron one by one. We group them into vectors and matrices. We use these blisteringly fast matrix multiplications, literally just multiplying a weight matrix by an input vector and slapping on a bias. This simple mathematical translation, it's the foundational building block of our entire network. Moving right along to step 2, making a forward pass. During this incredibly fast forward pass, data just flows straight from left to right. Our input data, let's call it X, enters the computation graph and gets multiplied by our first set of weights. Then it passes through an activation function, which creates this hidden representation. Think of that as basically the network's internal, abstract understanding of the data. This keeps passing through more and more weights until, boom, we output a final guess, known mathematically as y-hat. So at this point, the network has made its prediction based purely on its current understanding of the world. But, what happens when that initial guess is just flat out wrong? Let's get into part 3, navigating the loss landscape. And let's be honest, when a network first starts training, it is almost always hilariously completely wrong. So the network has to slow down and measure exactly how far off its prediction that y-hat was from the absolute truth, which is just y. It does this using a cost function, like cross-entropy loss. Now, without getting bogged down in the heavy algebra here, this formula fundamentally just spits out a single number telling the system exactly how terribly it messed up. Our whole goal in the training cycle? Shrink that number as much as possible. To fix this loss, we use a really clever method called gradient descent. Imagine a blindfolded hiker trying to find the absolute lowest point in this hilly, uneven terrain. They obviously can't see the bottom, so they just feel the ground with their feet, find the steepest downward slope, and take a step in that direction. Well, the network navigates the lost landscape in the exact same way, just endlessly searching for the lowest possible cost. By calculating this mathematical gradient, the network knows exactly which direction to adjust its weights to lower that overall error. The gradient gives us the direction of steepest descent, and a hyperparameter called the learning rate, or alpha, tells us exactly how big of a step to take. And this is a delicate balance. Take too small a step and training is going to take forever. Take too large a step and your hiker might just blindly bounce right over the valley to the other side without ever hitting the bottom. Nobody wants that. Which brings us to part 4, the calculus of learning. All right, here is the complete neural network training cycle in a nutshell. First, you randomly initialize the weights. Second, calculate the gradient of the loss. Third, update the parameters using that gradient and our learning rate. And fourth, just repeat steps 2 and 3 over and over again until the model is trained. Sounds simple, right? But the major bottleneck here, literally the absolute hardest part of this entire loop, is step 2. To actually find that gradient, we have to use the chain rule from calculus. Neural networks contain a massive, long string of operations, so the chain rule lets us figure out how a tiny, infinitesimal change in one early weight ultimately impacts the final loss at the very end of the network. And because we're dealing with vector-valued functions and matrices here, we actually multiply these derivatives from right to left, just to make sure all the dimensions match up properly.
But this brings up a pretty massive practical problem. Modern AI models can contain millions, sometimes even billions of parameters. If we tried to use basic numerical software to crank out these derivatives one by one, using something like finite differences where we calculate a tiny change for every single parameter independently, it would be disastrously slow. Not to mention highly inaccurate. It creates a total computational roadblock.
So how do we fix it? Let's dive into part 5, the magic of backpropagation. The elegant solution to this roadblock unveils what is arguably the most important algorithm in all of deep learning. Instead of calculating derivatives from the input forward to the output, which is known as forward mode differentiation, modern AI uses backpropagation. And backpropagation is essentially just reverse mode automatic differentiation. Rather than asking how one single input affects every downstream node, reverse mode flips it. It asks how the final single output, our loss function, is affected by every single upstream node. I actually really like to think of this as playing the blame game. By starting at the final error and working right to left, we figure out exactly who is to blame for the mistake. But here is the real magic. Because neural networks are made up of a sequence of so many functions, the chain rule requires all the later layers' derivatives to be multiplied together. So by working backwards, we just keep the already multiplied together derivatives from those later layers and reuse them. We share the repeated computations, which radically saves data and seriously boosts efficiency. To manage all this, software frameworks track every executed operation during the forward pass in a directed acyclic graph, or a DAG for short. In this graph, the leaves are your input tensors, which are basically just multidimensional grids of data, and the roots are your output tensors. Because the nodes correspond to the exact values we computed, we can seamlessly trace this graph from the root loss all the way backward to the leaf inputs. We automatically compute the gradients by applying the chain rule over and over again along this exact graph. It's a really beautiful piece of engineering. And in practical code, using software like PyTorch, all this incredible mathematical heavy lifting is handled completely behind the scenes for us. Calling a simple command like loss.backward triggers this entire symphony of reverse mode calculus across the computation graph. Then you just retrieve your gradients from w.grad. Plus, PyTorch lets you use the .detach method to disable gradient tracking on specific tensors. This is absolutely crucial if you want to mark some parameters as frozen, which speeds up computations massively. Actually, that's exactly why you can fine-tune massive AI models on a regular computer at home without needing some billion-dollar supercomputer. So, by mastering this continuous cycle of predicting, calculating the error, and cascading that error backward to adjust the weights, we've built the entire foundation of modern artificial intelligence. I mean, it's the exact engine that allows tools like ChatGPT to chat with you and Midjourney to generate those stunning pieces of art. But as we look at massive new architectures and billions of interconnected parameters, it leaves us with a fascinating final thought. If this elegant cycle of forward passes and reverse mode backpropagation built the AI of today, what revolutionary yet undiscovered optimization methods will build the AI of tomorrow? Thanks for joining me on this explainer of the neural network training cycle.